So can you guys see my screen? You just give a thumbs up if you can see my screen. All right. Okay. So yes, today's topic promoting data structures and algorithms. And for this particular conversation, I'll be focusing on time and space complexity. Right? Don't be alarmed. It will all get clearer in time. So yes, just to introduce myself, could you please just mute yourself? Sorry, so you don't distract others.
One sweet.
I don't know. I don't want to say anything last year.
Can yes, thank you. I was going to say that. Okay, so I'm a full stack web developer. I've been a full stack web developer for about 4 or 5 years now. I graduated with a bachelor's degree in computer science from FUNAB. Yay, if you know FUNAB. From there, I went on to work in AppZone, which now Zone. AppZone was a fintech, um, helped them manage like millions of transactions monthly. I worked as a backend engineer at AppZone. I'm also a Microvice alumni. Microvice is a tech school, sort of, where you learn how to write millions of algorithms and work with developers from all across the world. I made so many friends when I did my program in Microvice. It was a fun experience. Then I went on to also get a certification in full stack um, web developer or web development with Udacity. Currently, I'm a team lead at Quidax. Quidax is a cryptocurrency exchange market. So you can come there, buy and sell crypto, convert it to fiat, which is like your local currency. You can save in dollars. Basically, you guys can check out the app maybe after the call. It's pretty cool. So yeah, I'm also an ALX Code Fellow. That's I'm writing them. They will sue me if I don't do this. So there's that as well. And then in my private time, I am an anime and movie lover. I enjoy watching cartoons. I enjoy watching anime, and I watch a lot of movies. I'm easily almost always in the cinema. So yeah, that's it for me. So the table of contents we have, I'll be talking briefly about algorithms. I'll be talking briefly about data structures, then time and space complexity, big O notation, and then the next steps that I would expect you to take after this conversation. And then, of course, I will conclude. So, yes, algorithms. So, the first thing I would like to do is help you understand that these concepts are stolen or adapted from things you do every day. So, they are not things that you should be frightened of or afraid of. They are things you do every day. You're just not conscious of it. For example, I'm assuming that the majority of people here are students. So if you wanted to go to school, the question would be, how would you go to school? You will go on to say, I'd wake up in the morning, I have my bath, I'll make breakfast, I'll get dressed, then I'll go out. That's an algorithm because you have steps to solve a problem. Another example could be, how do you want to fry eggs? If somebody walks up to you and says, oh, I want to fry eggs, I want to eat fried eggs, I don't know how. And then you go on to explain how that person can make fried eggs in steps. You are describing an algorithm. That's what you're doing. So we do these things every day, right? It's just that in computer science makes it a bit more structured, right? So that there can be conventions that can be communicated across. What am I trying to say? For example, it would be ridiculous if somebody should come to meet us now and say he wants to measure distance by his legs, for example, because that's going to be an headache because the world has already come together and we've already agreed we want to use centimeter, millimeter, decimeter, and the rest. And somebody is coming to meet us to say, oh, they want to start using legs to measure distance. It's going to give everyone headaches. Why? Because we've all agreed to do something a specific way. So it's the same thing in computer science. So algorithms is a general term. They use it in engineering. They use it in all kinds of places. But computer science took it, did a bit of abstraction, a bit of tweaking, and they all agreed that that's how we're going to go about to solve things. So that's just algorithms in a nutshell. So in the context of computer science, algorithm is for solving problems that are suited for computer implementation, meaning You are taking those steps to solve problems and you're writing it in a language that a computer can understand and use it to solve that problem, right? So an example of an algorithm that you can give a computer to solve is all right for a computer to solve because the computer is garbage in, garbage out. Well, except today where we have a human writing most of the work, but we'll leave that. That's a topic for another day. So, for example, if I wanted to find an algorithm to find a number in a sorted array, right? So, I don't know if my VS Code is showing. Can you see my VS Code? Please give a thumbs up if you can see my VS Code. No, it's not sure. Okay, okay, it's showing now. It's showing now. All right. So, just to give visibility to what I'm saying. So forgive me. This is part of the conversation. I'll find ways to bring it in later, but this is what I'm trying to explain. So a sorted array. Sorry, this is a simple way to visualize a sorted array. So you just have an array with numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you want to check if a number exists in this array. So let's say the number is 12, for example. You want to know if 12 is in this array, right? So this is a problem that I have, and I want to solve this problem, but I don't know how, right? So to write an algorithm to solve this problem would be an example of algorithms in computer science context, right? So I wrote it down simply. I don't want to get into details, but that's not the point of this meeting. So I'm going to skip things along just to. I'm very mindful of time. I don't want to waste your time and all that. But if you have questions in the end, I can come back and then stress on these things, right? So just note your questions as we go. So I could just decide to start from the first index and then compare the value in the index to the number I'm trying to find. If the number equals the value, then I'll return true, meaning that number is in the sorted array. Otherwise, I go back to two. That is, I come back here. I increase the index by one, and then I come back to two. That is, I compare the number in the index, check it with what's in the array, and see if that number is correct. So I continue doing this until I get to the last index. So if I get to the last index and I can't find that number, then that number is not in the array, then I can return false. So this is like a step by step of an algorithm, right? I mean, I could implement it here, but I don't know. Is that something if you don't mind? Otherwise, if it's something too basic for me, I can just move on. Okay, okay, so, all right. So let me just do this real quick. So if I call this, so I like Ruby on Rails. So I'm writing in Ruby, but I'll write it in a way that is easy for everyone to understand. So it's pseudocode, right? So it's not particularly specified to any language, but it will look like Ruby. So just bear with me. So find number. It takes in an argument of an array and it takes in the number you want to find and then end. So I want to loop through the array. I want to loop through the array. So this is a loop. So this is array.each. So what this is going to do is going to iterate through every member of the array. So it will go from 1, 2, 3, 4, 5, 6, on and on like that until it gets to the end. Once it gets to the end, the loop will stop, right? Excuse me. So while I'm here, I'm saying return true if okay, now let me not use number because it will be the exact same thing. If value equals number. So it starts with 1. It checks, is 1 equal to 12? No. The loop comes to the end, goes back. It increased the index by 1, meaning we move to the next index. What is in the next index? 2. It checks, is 2 equal to 12? No. The loop ends, goes to the next iteration, increases the index by 1, goes to 3. It checks, is 3 equal to 12? No. It continues and continues and continues. In this case, it's not going to find the number there. So it's just going to return false, meaning it's not there. But assuming at any point any of these numbers was equal to the number we're looking for, which in this case is 12, it would have returned true. This is an algorithm. Very simple algorithm to find a number in a sorted array. If the array was not sorted, that would be an entirely different headache. But yeah, this is a simple case. So this is a simple example of an algorithm, right? There. So on to the next slide. Excuse me. So we have popular algorithm types. Bukola, your hand is up. Is that, do you have a question? Okay. So popular algorithm types, we have brute force. So brute force is anywhere anywhere belief is. It's just you basically saying, excuse me, it's just you basically saying this is the fastest answer I can think of, right? For example, if somebody wakes you up in the morning and says to you, "Oh, you need to get to K2 today. There's something urgent you need to do." You're not going to think about having your bath. You're not going to think about brushing your teeth. You're just going to rush in, get dressed, carry your bag, and just dash out, and just find your way to K2, right? That's a simple example of a brute force algorithm. You're not thinking about a lot of things. You're not considering a lot of things. You just want to solve the problem. You don't care about anything at that point. You just want the first solution that comes to your mind. Excuse me. So that's brute force. That's a brute force algorithm, right? So for a beginner, you would most likely be coming up with brute force algorithms for most of your coding challenges and stuff, right? It's fine. It's okay. You're just learning. But as you start to grow, you start to consider several things while writing your code. And some of those things that you consider is part of the conversation in this class. So another type of algorithm is a recursive algorithm. A recursive algorithm is an algorithm that calls itself to solve a problem. Right? You just keep going deep down into the solution to solve that problem. For example, an easy way to visualize a recursive algorithm in real life is having like a help, like a housemaid. You don't do all the work in the house, right? So, but you hire someone to do the work, and then you give that person instructions that, oh, I'm hiring you to do this, but so do this, and then you move on with your life, right? Because you've given that responsibility to someone else, right? So each time that person sees that problem, and that problem is going to happen several times, right? For example, if you want the person to cook for you, you eat at least 3 times a day. So the person is just going to pick up the problem, solve it. The next time, pick up the problem, solve it, until the problem keeps getting smaller and smaller and smaller and smaller. So that's an example of a recursive algorithm. It's solving a problem by, okay, yeah, I'm definitely going to need water. Just give me a minute, please. Right, I'm back. Sorry, the boss is here with me, so I won't have to go for next time. So yeah, that's an example of recursive algorithm. So if you want to check recursive algorithms, you can look at Tower of Hanoi. You can also look at Fibonacci sequence. Those are like the simplest examples that they usually give in computer science for recursive algorithms. So the algorithm just calls itself on itself to solve a problem. I used one recently in the office. We're trying to validate the keys in a hash, but it was a very big hash file, and we're trying to validate it. And I realized that since I'm going down, the algorithm just kept calling itself until it traced through all the keys, both the outer keys, the inner keys. It just sweeps all through. So just to let you know that having this knowledge is very, very useful, right? Because you find problems and you have to solve them. So it's not easy to just never think about it. You just have to solve it. So just the details. You just want to illustrate an example to just let the person realize that, oh, this algorithm can work or this approach can work. You can use brute force. Just do the demo. The person sees that, oh, everything works. Then you just realize that yes, this stuff works. Then later you can clean it up and make it much more efficient, right? So a greedy algorithm is similar to brute force, but the difference is greedy algorithm is usually for a large data set or a large scale of data. For example, Google Maps will use something like greedy algorithm. So you want to get from A to B, but there are different ways to get there. So Google Map won't stop to think about weather or the number of cars that will probably be chasing you. Google Map won't check fuel. Google Map won't check the money in your account. Google Map won't check all those details. It won't pay attention to all those details. It just restrict itself to specific parameters, the length of the road, the speed you will most likely be moving at. It will restrict itself to certain parameters and then just give you an evaluation, right? It won't try to consider too many things. It should just look into a fixed number of parameters and then give you an evaluation. That's a greedy algorithm, right? It's used mostly for graphs. And graph data structure is for nodes that are connected to each other. For example, countries or roads. One links if you want to go from Yaba, you can probably go from Yaba to the island. You can go from Yaba to Agegi. You can go from Yaba to Surulere. So all those points are linked. They are all linked, right? So really algorithms are very good for those kind of problems. Then you have backtracking algorithms. So backtracking algorithms are how computers are taught to play games. A good example is chess. So the algorithm is responding to the opposite player. Once it makes a mistake and you beat it, it takes a step back. It notes that that decision it makes is wrong. It removes that decision from the options of choices it has to make, and then replaces it with another one. So backtracking algorithm is like how children learn. So you learn by mistakes. A child sees something sharp, picks it up, it hurts the child. The child notes it, and then the next time, the child knows that if I pick something sharp, it's going to hurt me. So it's going to make a different decision because when it made the decision to pick up that sharp object, it got hurt. So that's how backtracking algorithms work. There's always an option of choices or an option of decisions. If anybody has ever played chess, there's always an option of choices. It notes the option. It's a very interesting way to write code. And the first time I saw a video on it, I was fascinated. So I think it's also similar to how machines learn. It's also similar to machine learning algorithms as well. So you also have divide and conquer. For divide and conquer is basically break the problem into two. Solve it on one side, solve it on one side. When you are done, bring it back together. And lastly, dynamic programming. Dynamic programming has to do with, is similar to caching. So caching in development is you are saving a solution so that the next time you don't have to think about the solution. Just go and pick that solution up because you've already done it before. There's no point calculating something you've already calculated before. Just go and use that value instead, right? So a good example to put all these things together is if you want to check if for a phone number in a telephone book. Back then, not like today now that you have, all your contacts on your phone. Back there was like a directory where you have to search for phone numbers. So brute force would be you are just skimming and scamming, trying to find where the number is. If it drops anywhere you land, anyhow, like most the way most people read their Bibles, where you just like, God just speak to me, and you just open it, right? That's like brute force. Anyhow, we will get there in the end, right? A recursive algorithm will be a situation whereby you, for example, you start with like smaller books or smaller phone books. So instead of picking like a very very big directory, you start with like a smaller directory, and from that big directory, sorry, you go to a smaller directory. So each time you are reducing the size of the book that you are going through, just hopping, you know, At one moment, the problem is very big. You make the problem smaller. You make the problem smaller. You make the problem smaller until you find the phone number you're looking for. So grading algorithm in the case of a phone book would be similar to brute force. So somebody told you that, oh, just go and check page 300. You will most likely find it there. So you just go straight to page 300. Why? Because that's the fastest solution based on someone else's analysis, right? So you just pick up the book and you just go there straight because somebody has done it before and told you that that is your best chance, right? That's a greedy algorithm. A backtracking algorithm in the case of a phone book would be you going to, like, maybe you're looking for the phone number will be in Z. That's like the end of the page. But you started with C. You got to C, you saw that C wasn't it, so you remove C from your options. You go and check another section of the phone book. You get to the section of the phone book, you see F. It's not there. You remove F from your options and continue like that. So each time you're not looking at the entire book because you're reducing your options, your choices, or your decisions in that context. So divide and conquer in that case will be um, dividing the book. So if you know that the book is indexed, so you have, let's say for phone numbers, you have it's tied to the person's name. So alphabet, so A to Z. So you just know that the person's name is Cyril, for example, which is my name. I know that Cyril is C. So Cyril should be in like C section. So you've already removed like half of the directory out of the scope of your search because you know that it's not there. Note that you are able to do this because the data is sorted. If the data is not sorted, it's not going to be helpful, right? But because you know that it's sorted from A to Z, it's easy for you to just go to C straight because you know that Cyril's name is in C, and then you ignore D all the way to Z. You've divided the problem based on an index, right? It's very important to note that indexing because if the indexing is not there, you're not able to make that decision. You'll be making a guess, a calculated guess. So if you do databases a lot, that's why they tell you to index your columns. If you've ever dealt with a database before, that's why they tell you to index your columns because it makes it easier to find the data. Because the database won't have to do like a full table scan. It will just go to a section where that index is to go and look for that data there because the data is indexed. That's divide and conquer. So dynamic programming in the context of a phone book would be somebody has already checked the phone number before, so they've circled it. The person has already circled the number, so you just have to find where the person circled it. That's dynamic programming because you are dealing with a saved response. Somebody has gone through the problem, found the problem, and saved the problem. You're just going there to pick up the value that the person solved. So yeah, that's it in plain English. I hope that makes sense. Again, if you have questions, please just hold on to them. I'll address them in time. I'm just trying to speed things up. So yeah, take your breath. So again, these concepts are probably new or a lot. Don't rush yourself. Just take it in one at a time, right? It'll make sense in the end. So data structures. Now, a data structure is a storage for data along with defined operations to perform on the data it stores. Don't overthink it. It's just basically a sort of component or a sort of structure that the computer uses to store data and then defines operations that can be performed on that data. An example is an array. This is a typo. A linked list, a stack, a queue, hash, graph. I don't want to go into the details of all these things. So hopefully, excuse me, we'll have subsequent classes so I can break these things down individually. But just know that that's what data structures are. For like an example, an array. An array has operations. You can add it into the array, you can remove from the array, you can use indexing to find a value in the array. You can, you can adjust an array to behave like a stack and a queue. So a stack is like your dishes. The last thing that comes in is the first thing that goes out. Your queue is like your bank. When you get to the bank, the queue in the bank. First in is the first out of the queue. You might ask yourself, how is this useful to anybody's life? For example, your, your, undo. Your undo. Your undo is like your bank. When you get to the bank, the queue in the bank. First in is the first out of the queue. You might ask yourself, how is this useful to anybody's life? For example, your, your, undo. Control Z. So each change you make is saved in a stack. So you change something, the last thing you did goes to the top of the stack. So when you want to undo, you just pops the stack, so it removes that change. So it makes it easy for you to find the last thing you did first. So it's very useful, right? A queue for queue now, like in my where I work, any data that comes in, we queue it up. So there are workers waiting for whatever comes out of the queue first. So the first data that comes out of the queue, it picks it up, does whatever mutations it wants to do on the database, updates the database, send a webhook, etc., etc., etc. But all that functionality is built on a queue. I don't know. Did someone raise their hand? Or was that a mistake? All that functionality is
No,
built.
that was a mistake. Sorry.
All right, cool. All that functionality is built on a queue. If you ever heard of event processing systems like Kafka and the rest, they are just fancy queues essentially because data goes in, the first thing that goes in, first thing comes out. Although there are some additional processing they can add to it to like make it a priority queue, for example, if you want to deal with some data ahead of others, which is not different from what you see in a bank. Like when a rich man walks in or somebody that is highly connected, the person can jump queue. That's a priority. So the person in that context is in a priority queue because they are more important than everyone else. So the bank attends to them first. So you see what I'm saying? All these things, they are gotten from everyday life. Like every single one of these things, they are gotten from everyday life. They are not from the moon or they are gotten from everyday life. If you can really sit down and think about it, there are things you do every day. You just take them and build complexities and structures on them. That's they are just what you do every day, right? So a hash has indexing, right? So an index that maps to data. I won't go into details right now. A graph is like what I illustrated before about countries being connected or cities being connected or streets being connected. Every point on the graph or every member or every data in that graph is linked to several other data. So it's like a spread. It's just spread out. One point is can be joined to like 10 other points. Another of those 10 points can be joined to another 10 points. So to traverse, they call it traversal. To traverse a graph is a very interesting algorithm, but that's not for today. It will mess with your head. But if you understand it, great for you. Great for you. But don't worry, one step at a time. So yeah, the basics, the cocoa of data structures. It has operations. So know the operations of the data structure. There are times when a stack is useful. There are times when a queue is useful. There are times when an array is useful. When you need to use a hash, don't use an array. You might have problems because they have advantages and disadvantages. One might be easier to search through. Like it's easier to search a hash than it is to search an unsorted array, right? So when you need to do searching and you know that the data is not sorted, you might just want to subscribe to use a hash, right? It will make your algorithm faster. As opposed to somebody that doesn't have that knowledge, and the person will just be like, array is the easiest thing that comes to mind, and the person writes an array. It will work for 5 users, it will work for 500 users, but when you start to entertain your algorithm, you might not know what happened. But it's simple decisions like this that make all the difference. That's why it's important to know their advantages and disadvantages. But I won't be covering
That's
those
can be.
details on this call. So the hierarchy of the data structures. So you have non-primitive data structure, you have primitive data structures. So the non-primitive data structures are the data structures that other data structures were put together to make them. Don't overthink it, right? Don't just overthink it, right? If you want to build a house, you have blocks. The block alone is an entity. It can survive on its own. It can do things. You can use it to beat somebody. You can sell it to make money. It's an entity on its own. So it has its own data. It has its own properties. But when you put blocks together, you form a house. And the house now has its own operations. It has its own entities. Think of it like that. So primitive data is as cellular as you can get. It's as basic as you can get. The non-primitive data structures are the ones that other primitive data structures were put together to form, right? For example, a linear data structure like an array can hold integers. Some arrays can hold floats. Some arrays can hold characters. Some arrays can hold Boolean data types, right? And although depending on the programming languages, there are some programming languages that you can only create an array of a specific type, meaning it doesn't allow you to have dynamic arrays. So if your array contains integer, you can only put integer in. But there are some languages that can allow you to, like Python, Ruby, they can allow you to put all kinds of things into your array. They don't particularly care, right? So these are important things to note as well. And then you have your non-linear data structures like the tree, the graph, and the hash tables. So those are the ones that data can be connected in pretty different ways. So it's not linear. Linear means I'm here, the next guy is in front of me, the next guy is after the next guy. So you can just plot it like in a straight line, right? But for non-linear guys, a tree, I'm here, the next guy can be to my left, another guy could be to my right, another guy could be in front of me. So I'm connected to three other data structures or data types in that data structure. So yeah, that's what makes them non-linear. So again, not in this context. This is just me giving an overview so that when I start talking about time and space complexity, you can go along. So we can get into these details some other time. So benefits of learning algorithms and data structures, you get better at problem solving. Like I gave an example. Like I gave an example. In my company currently, we had an issue with the webhooks we were delivering, and we had to refactor the entire process because we were just picking up data from the database, and then after picking up that data, we put it into a loop, and we're just for each value in that loop, we send the webhook. But if one was slow, so basically we put all the webhooks in a queue. First in, first out, right? First in, first out. We process that one before we pick up the next guy. So if nobody's going to pick them up, nobody's going to attend to them. Similar to what you see in a bank queue, because you have a queue mapped to a single worker. So a single teller is at the bank attending to everybody on the queue. So if he's not done with the first guy, the second guy won't get attended to. So we have to refactor. So what we did was we mapped the queues, we mapped several queues to several workers, right? And we stopped picking directly from the database. So instead of picking directly from the database, which in this context would be people coming to the bank directly, just send your details, right? We put up a structure that would allow you pass data. So you don't have to come physically because it's a lot of work to go to the database and get data out. Just send your ID, send your phone number. We know that we get your phone number, we know you have this issue. So we just put a representation of that data in the queue, which makes it faster because it will move quicker. So when that representation gets to whichever instance of the worker that picks it up, meaning we have more than one teller. So he picks it up, attends to the guy. But while he's attending to the guy, the next person will just go to the next free worker rather than wait behind the one that is being attended to. So we increase the number of workers. We also increase how the data was being sent. Things got sweet. Things got softer, faster. How did we know that? Data structures and algorithm, right? So it also helps you write better software. It improves your productivity. You solve problems faster. It also boosts your confidence as an engineer. So when people are talking about problems, you most likely want to, join the conversation because you have a thing or two to say. It also makes it easier to employ. So I don't believe you should stay in a company for too long, right? So even as I'm in my company now, I'm actively interviewing with other companies, and on most interviews, these are the kind of things they ask. Like I was showing you this code. So this process log code. My last interview, I was given a document and I was told to pass this document. And from that document, I was told to make certain reports. I wrote this thing live with the engineers. Oh my God, 6 minutes more. Waiting for me. So yeah, just to give you an example of how this information or this knowledge helps you, right? So going on. So time and space complexity, you need to know how fast your code can run. You need to know how much space your code can take, right? It's very important. It gives you an idea of how to write better code. So in order to do this, computer engineers came up with a process called big O notation. Big O notation is just a standard way of evaluating your code, from face value. You don't need to. It's not about, so it's machine independent, because a code you can give me might have headaches on my laptop, but if you take it to a bigger computer, it might run smooth, right? So said we as if I was part of the conversation, but they didn't want to have to deal with all those differences in machine quality or machine resources. So they came up with a very simple system to be able to tell how fast your code will run, how efficient your code will run. So on an overview, it's called Big O notation, right? Now, looking at looking at these two codes, I'll just, which one do you think? So let's call this guy A. Let's call this guy. Let's call this guy A. Let's call this guy B. Which one do you think will run faster, A or B? You can drop your contribution on the chat. Which one do you think will run faster, A or B? B. Okay, we have a B. Who else? Guys, which one do you think will run faster, A or B? A. Thank you, Akim. So thank you, Samuel. Thank you, Akim. Who else? Okay, we don't have much time, so that's fine. ATC community. Why do you think B will run faster? You're the one that has a contrary opinion. You can unmute and answer, please. Are you there? Can you hear me? If you're talking, you're muted. Okay, I'll just move on. So actually, B is faster. Uh, so I will just explain here because I have very few minutes left. I have very few minutes left. So this might be the last slide. There are a bunch of other stuff I wanted to show you guys, but I don't have that much time. So I'm just going to use this one to explain. So now, big O notation is all about trying to read and understand what's happening in your code so that you can make an evaluation. For example, in this, in A, I'm looping through the entire array. So I'm going from the start of the array to the end of the array, trying to find that number. So if the number is not in the array, I will end up going through the entire array. So I will do n operations. So if the array is like 1,000, for example, that means I have to check 1,000 values just to find one value. It might work very well for a small array. If the array size was 10 or 20 or 30, it will work beautifully, it will work perfectly. But when you start have to have like a very big data set, you'll just start noticing your data isn't running properly because it has to look through everything. So when you're writing your code, think of worst case scenario. The best case scenario is that the very first thing in the array you check is your number and it will return it. That's the best case scenario. But it's not always like that. So to write better code, think of the worst case. The worst case is that either the number is the very last number or the number is not there at all. In which case you have to do n operations, which is a problem. This one, on the other hand, this is an implementation of binary search. So it's a divide and conquer algorithm. So what this guy is doing is, because this array is sorted, it starts by checking the value in the middle. So let me illustrate it with this one. Let me illustrate it with this one. Let me illustrate it with this one. Yeah. So it starts by checking the value in the middle, which in this case, let me just make it odd numbered so it will be easy to spot out the middle. So it starts by checking the one in the middle, which in this case is 6. Which in this case is 6. So it checks, is 12 bigger than 6? Yes, 12 is bigger than 6, which means the number will be on the right hand side of 6. So it checks this one. It picks the middle. It picks the number in the middle, which is 9. It checks again. Is 9 equal to 12? No. Is 12 greater than 9? Yes, which means 12 will be on the right hand side of 9. So it picks these guys again. And then it does the same thing. But in this case, 12 is not here. So if 12 is not here, 12 is not in the array because this is the largest side. So it just returns false. How many operations did we do? Just three. Just three operations. So we just did one, two, three, and we found our value and returned it. So if this was a very big data set, the number of operations would be smaller. But if we had done like the first algorithm that had like lesser amount of code, it would have started from 1. 1 is not equal to 12. Check 2. 2 is not equal to 12. Check 3. On and on and on and on and on till it gets to the end. So by the time it gets to the end, it has gone through the entire array. So imagine how much time this will take. So in this case, the O of n, or the big O notation for this particular, is O of n, meaning, and in a worst case, you always have to look through or do n operations because you're checking the array and you're going through the entire array. So you're going to do n operations. And in this case, we'll probably need another time and another class and more time to really delve into these things deeper. Like really give the full wealth of what I was trying to say or what I am trying to say. So this is log n. Now is log n heuristically or simply, there are deeper explanations, but I don't want to get into that right now. Is log n simply because we have reduced the amount of search we have to do or the amount of operations we have to do. So meaning the bigger n gets, the lesser operations we would have to commit. We won't have to do as much as n operations as n gets bigger. But in this case, the bigger n gets, that's the bigger the size of the array gets, the bigger the amount of operations we have to make. So this is better. So these are the advantages of having this knowledge. So it helps you tell easily which code will perform better than the other, right? So yeah, let's go on. I don't think I have this slide. So yeah, big O note is a computer science equivalent of share this thing will make sense. So that's why you're just looking at it and like after you've written your code, you sit back and think to yourself, would this thing make sense? Then you do the calculations and see for yourself if this algorithm will perform better. And if you see that it's not going to perform better, it's an indication that you probably need to rewrite your code. You need to go back, sit down, relax, and think about your code. Or if you can't find something better, you can bring on a more senior engineer to sort of, have conversations around this thing so you can come up with something better, right? So you can start with the brute force, it's fine. At least it shows that you understand the problem. If you're able to find a brute force that can work, it shows that you understand the problem. Then from the brute force, you can now sit back and start to consider other ways or other things that can make it faster. So yeah, so it gives a standard way of how your code is fast and how much additional space it might take. And in mathematics, it's called asymptotic notation. So you might want to, if you want to do more research, you can check that out. So the calculation of the big O notation of an algorithm, we typically make some assumptions. So we treat any assignment as a single operation. No matter the amount of assignments you are doing, it's just one. We don't really count assignments as anything. It's loops we tend to pay more attention to, right? Unless you are probably doing that assignment in a loop, which means you will do that assignment n times. So there are situations where it's best to do the assignment outside the loop and just keep changing the value of that variable rather than always reassigning the variable inside the loop. I'll show you examples of this in our probably subsequent classes, just so you guys can have better ideas of these things. So constants are constantly being ignored. So 2n squared is still n squared. So let me just go on. Let me just go on. Let me just go on. So I think we're just going to need another class. Let me stop here today. Yeah, no problem. Okay.